All right, so now I think what I want to do is I want to talk a little bit more detail without trying to bog us down too much into what it means to align these electrons. All right, this is going to be a little tricky because it's a quantum effect, and so I'm going to draw pictures that are not true quantum pictures, but they can still give us the idea. Remember that we said that basically if you have a coil of electrons that are circulating in this coil, what we can do is we can get a concentrated magnetic field inside the coil. So if you just consider, forget a coil, just consider a single electron moving in a circle. Like if you could just grab it with your finger and move it in a circle, it should generate a magnetic field pointed in a certain direction. What would that look like? Right? That's what I want to talk about next. What would that look like? Let's say we have an electron moving. I'm drawing kind of a side view here, kind of in this direction like this. Right? And that means at one moment in time, the electron is right here. It moves this way, it moves this way, and then the electron later in time is right there. And these arrows are not magnetic fields. It's the direction. I guess I'll shade them so that we don't get them confused with magnetic fields, right? It's circulating like this. In other words, imagine it just kind of going around in a circle like this. And we know that moving electrons generate magnetic fields. How and what direction would it be generated in? Well, first of all, I want to talk about something called angular momentum, right? Or spin, right? So the spin axis of this thing, you could think of the spin axis of this thing, call it S, so the angular momentum. In the direction of travel, you have an angular momentum pointed perpendicular to however the thing is rotating. We call that the spin, or you can also think of it as angular momentum, right? If I wanted to figure out how the magnetic field was pointed here, I would use the right-hand rule. But remember, the right-hand rule deals with positive currents. Everything has to be reversed when you're talking about electrons. So if I put my finger into the board, if the thing is going this way right here, that would be positive current flow, but the electron is really going in that direction. So what I would do is I would turn my finger around and say the positive current would be going the opposite direction of the electron. Remember, the right-hand rule thumb points in the positive current flow. So if this thing is going like this, it's going into the board here, but then I have to turn it around because the positive would be going in the exact opposite way. That would mean that I would have a magnetic field circulating kind of like this around. It would basically be going down and then kind of like back up through here, right? At this point in time, if again, it's coming out of the board, which means I go into the board here, then I'm going to have a circulation and a magnetic field that's going to be going down like this, and then this way it's going to be going the opposite way. It's like one little loop of the coil that we had just talked about right here. And notice that these are kind of additive, so we get a strong magnetic field in the middle and a kind of a weak magnetic field everywhere else. Now, if you can, this is why I said I'm lying to you a little bit, because electrons are not little balls. Okay, electrons obey wave mechanics from quantum mechanics, but you can still think of them classically as little balls, and it helps us visualize it, but just know that I'm lying to you a little bit. They're not little balls, but classically we can envision them like this, okay? So don't get too mad at me. I'm just trying to make it easy for you to understand. If we make the radius of this thing smaller and smaller, but keep orbiting this electron, then what's going to happen is we're going to get a very concentrated magnetic field on the inside as we get it smaller and smaller and smaller. What happens if we make the radius of the thing so small that really it's not orbiting, it's just like a ball rotating? Would the electron have a magnetic field associated with it? The answer is yes. Every school child learns that electrons and protons have charges and they repel, electric repulsion. Either they repel if they're the same charge or they attract if they're opposites. Opposites attract, right? But most school children are not taught that electrons also have a magnetic field associated with them. We can measure it very, very accurately. It's called the magnetic moment of an electron. And even though we know electrons are not balls that spin, we can still envision it in this thought experiment, an orbiting electron getting smaller and smaller and smaller. Eventually, what it is just a single electron that is kind of like rotating, even though it's not rotating. But if you had the radius of it getting smaller and smaller, eventually it rotates, then there should be a magnetic field associated with this. And the magnetic field that we measure for electrons is a fact, and it behaves kind of, as you can think of it, as an electron spinning. So we say that electrons have spin. Now, it doesn't really mean that electrons are balls that spin. What it really means is electron is this thing that nobody can really visualize, but it obeys wave mechanics, and they have angular momentum, which means they have a spin axis, and they have a magnetic field oriented in a certain direction, somewhere along the line of that spin axis, right? So if we do the right-hand rule and figure out that these things are essentially, if it's kind of going this direction, the magnetic field is pointing down in the center here. If you shrink the radius of this thing, then I'm going to take the little arrow away, and I'm going to put the, I guess I'll put it here. This is an electron, right? Here, then what we can say is that electrons behave as if they are spinning, and they have a sort of a magnetic field that emanates from this, or from them, and as you might guess, looks something like this, right? Now, this is not an exact picture or anything like this, but essentially they behave like this. So you have pointing like this, pointed like this, right? So if you look at it, it's almost like down and then up, but if you shrink it down, it's like along the spin axis, it should be pointing down, and so along the spin axis, it's pointed down, and so they're coming down out like this, right? And they kind of go back into the other side. So it's sort of like just shrinking down this concept right here. So there's a lot of things going on inside of an atom. We have electrons surrounding the atoms. Those electrons we say are orbiting, but that picture of a solar system of orbiting like planets is not really true, but it's still good for us to visualize the general idea. There is an angular momentum of the electron cloud around an atom. That's what we can say is true. And that contributes to some magnetic effects. But more dominant than that is that the electron, even just by itself, spins all the time. Now, it's not really a ball spinning, but it has angular momentum, right? It has angular momentum, and so it has a spin axis we can label here. And then it has what we call a magnetic moment, which is going to point down. This magnetic moment of the electron points down. We call it mu sub s. This is the magnetic moment of a single electron by itself, not near an atom, not near anything. It appears as if it's a spinning ball. It's not a spinning ball, but that's a good way to think of it. And it has a magnetic field oriented opposite to the spin axis. The reason it's oriented opposite is because the right-hand rule is for positive charges, but electrons are negative, and so the axis is flipped opposite. Exactly why I spent time on the right-hand rule earlier. So in ferromagnetic materials, what we say, or what the theory is that the electrons that are in all of the atoms in a ferromagnetic material are very easily, or much more easily, able to be aligned. What it means is the spin axis of all of these electrons are able to be aligned. And that means the magnetic moments and the magnetic fields are all able to be aligned. So if you can imagine trillions of these electrons everywhere in the material, and they're all lined up like this, then the magnetic fields will be additive, just like they're additive inside of the coil, and then they'll eventually exit the whole thing and come back around and enter into the other side. And this is why if you break a magnet in half, there's a north and a south pole. So you think, okay, I'll just break it in half. What will happen? Well, then you have a new north and a south pole on each piece, because there's not just a north and a south pole. There's almost an infinite number of north and south poles. All the little electrons are forming kind of a tiny little north and south pole bar magnet. You can almost think of each electron almost being like a little bitty bar magnet inside. So if you break it in half, all that's going to happen is the field lines are going to connect to wherever it broke off. So you can never get down to a single, you'll always have closed loops, I guess is what I'm trying to say, even if you break the bar magnet in half. All right? So the picture that we often draw is in a ferromagnetic material, right? Like a bar magnet or something like this. Then below a certain temperature, or if it's not magnetized already, the spins of the electrons are basically in all the material, they're just randomly lined up in different directions, right? But if you apply a magnetic field to this material, or if the Earth does it, because the Earth is a permanent magnet, right? Then what you can end up doing is you can end up aligning them in the same direction. Now, in reality, they're not all lined up in the same direction, because remember, everything is at a certain temperature, everything's being agitated. So thermally, there's collisions happening and things are being knocked out, but still there's an overall alignment happening in aggregate across the material. And that makes the magnetic field emanate from one side to the other. And it's because of the quantum mechanical nature of electron behavior. So there's a tiny contribution from the orbiting of the atom, We call it the orbital angular momentum, but there's a larger contribution to the spin angular momentum of how electrons behave. So that's what effectively ferromagnetism is. Any bar magnet has already been aligned and it retains that magnetism. But if you heat it up too much, thermally, it'll start to be unaligned again, and you can demagnetize a magnet that way. All right? Now, let's talk about, let's see, I talked about that. Let's talk about another kind of magnetism you may have heard of called paramagnetism. So the prefix para, I looked it up, it can mean lots of things, like 10 different things, but it can mean beside, it can mean near, beyond, or abnormal. So think of paranormal as like abnormal. So paramagnetism is sort of like abnormal magnetism, or you can think of it as near magnetism. There's many different meanings for the word para. Paramagnetism is simply induced magnetism. Just like we can take ferromagnetic substance and line them up and they'll retain their alignment because of I've kind of skipped over a lot. The reason iron can do that, the reason iron can be aligned that way is because of the way the electrons are paired up in the material. At the quantum structure of the electrons orbiting the atoms are paired up in such a way that allow them to be aligned like this. Most materials cannot be lined up like this, and so most materials are not magnetic at all. Well, at least they're not ferromagnetic. Many materials can be what we call paramagnetic, which means that if you apply a magnetic field to them, they can be aligned, but only weakly. Right? And when you remove the magnetic field, they immediately go back to their random state and they're unmagnetized. Many materials are like this. Examples are tungsten, aluminum, lithium. Typically, if you put a magnet next to an aluminum can, it won't be magnetically attracted, but aluminum is weakly paramagnetic. So if you put it in a strong enough magnetic field, it will align and turn magnetic, but only weakly. Again, the electronic structure of the electrons orbiting the atoms govern this behavior. It's beyond the scope of this lesson, and you study quantum mechanics and chemistry, we'll learn exactly in the electron configuration why some materials are magnetic and some aren't. But it has to do with how the electrons are in the orbitals of the atoms and how they're paired up. So, paramagnetism, alignment of the magnetic moments of the electrons when an external magnetic field is applied, but again, it's a weak alignment, and when you turn off the external magnetic field, the effect goes away, and so then it just loses all of its magnetism. All right, we could talk about paramagnetism and ferromagnetism forever, but I think I want to be done with that for now. I want to tackle the concept of why do magnets attract and repel. I'm going to say right now that no matter what I tell you, someone is going to email me and say it's wrong. And that's because there's multiple ways of thinking about why this effect happens. Ultimately, magnetic attraction is purely a quantum mechanical effect. And we don't have everyday experience with that, so everything at the quantum level seems like it's unnatural, but in fact it is natural because everything is made of quantum objects, ultimately, right? But the way I'm going to teach you about it, I think is a good way to think about it, but just know that there are other ways to think about magnetic attraction. You can even use Einstein's theory of relativity, believe it or not, to describe magnetism. Now, I'll do that maybe another day. But for now, I want you to have an intuitive understanding why magnets attract each other and how they can repel each other. All right? Before I do that, I need you to understand something. The magnetic energy density. I promise it looks complicated, but it's actually very, very easy to understand. Magnetic fields store energy, right? They store energy. And when you can extract some of that energy in some of our modern devices like generators and things like that. But they contain potential energy. Electric fields also store potential energy. So the equation that governs that is the following. The magnetic energy density is equal to the magnetic field strength squared divided by 2 times this constant, the permeability, which I mentioned several times applies to magnetism. Only thing I care about you knowing, I don't even care about the units, although I'll tell you that the units is basically going to be joules per some unit volume, right? It's an energy density. So the magnetic field, you square it, and then you divide by 2 numbers. This is a number and this is a number. So basically the energy density is just related to the magnetic field strength squared. The higher the magnetic field, the more energy it stores, right? We can build electronic devices, coils of wire that store lots of energy in magnetic fields that can be released in, in other situations, right? In circuits, for instance. The best way to think about stored energy is a rubber band. If I pull a rubber band, I'm storing energy in that rubber band. How is it stored? In the electric attraction between the atoms, which are now being stretched apart. It's wanting to pull them back together. So there's energy stored in the electric field between atoms and electrons, and there's energy stored in the magnetic field that exists in space. And where the magnetic field is strongest, then the energy is going to be higher. So if you think about it, around this wire, out here far away, the energy stored in the magnetic field is small, but the energy density is very high, very close to the wire. The magnetic energy density is very high inside of the coil, but very weak outside for the same reason. Now I need you to understand that in order to understand why magnets attract and repel each other. So here we go. It's going to be easy to understand, I promise. Here is a bar magnet, right? Here is another bar magnet. All bar magnets have some north and south pole. I'm going to draw this one north-south. I'm going to draw this one north-south. Now, how are these things going to behave? Same poles are going to repel each other. We know that to be the case. Let's draw the magnetic field, not the whole field. We'll just draw kind of a little portion of it. It comes out of the north, goes into the south. So this way, this way, this way. It goes out of the north, into the south, right? This one is going to go this way, and it's going to connect again to its south pole, out of the north, like this, and in to the south. Right? Now what's going to happen as we push these things closer together? Notice that the direction of these arrows are kind of pointed at odds with each other, but the closer I get them, what's going to happen is they're going to be sort of additive. Yes, you can think of it as a vector. You can think of it, some of it pointed this way and some of it pointed up. So you are going to have a cancellation in the portions that are pointed at each other, but you are going to have a portion pointed up. And as you get them closer together, that's going to get bigger and bigger and bigger. So they're going to be additive inside. They're in general pointed in the same direction. So you're going to have strong field inside of here as you push them together, because you can see they're sort of pointed not exactly in the same direction, but as they get closer together, they're going to be more and more, if you can think about the ones coming this way, they're going to be aligned up more and more, and it's going to get very, very strong magnetic field in the center. But the stronger the magnetic field, the more energy is stored. So you have to think about, how does the universe operate? The universe operates by going from high energy to low energy. This marker has potential energy from the gravitational field of Earth. Here it is at a high potential energy. When I let it go, it's going to move down to a lower potential energy because it's closer to the ground. Everything in general wants to travel towards lower energy. If you start asking me questions like, well, why does everything try to go to lower energy? I am sorry, I can't help you, but that is how our universe works. The rules that are in place are that things tend to wind down towards lower energy. When you drop things, they go from high energy to low energy. When you have temperature, a very hot cup of water, it tends to cool off because it's going from high energy, high movement of the atoms, to low energy, low movement of the atoms. When you stretch a rubber band, that's high energy. You let it go, it goes to low energy state. And if you try to push these magnets together, it's going to be trying to make a stronger and stronger magnetic field in the center, which is going to raise the energy of the energy stored there. And the universe never wants to go to a higher energy state. That goes against the laws of nature. So when you put two magnets together, because the magnetic field is trying to get stronger in the middle, storing more energy, it's going to resist that. In other words, I have to put work in to store the energy there. Let me say that again. I have to put work in from my chemical reactions in my muscles. I have to do work on the magnets to store the energy that is now higher between the magnets. Because when I put them together and force them together and hold them there, then I've now stored energy in the field. Where did the energy come from? It came from my muscles. Where did that energy come from? It came from the food I ate. Where did that energy come from? The chemical bonds of the food I had. So the energy came from somewhere, the food, and into the magnetic field. When I let it go, they tend to push apart because the energy is then released, and everything, the universe tries to move towards lower energy states. Just like the marker goes from high to low, the child on the slide goes from high to low, the rubber band goes from high to low, the cup of coffee goes from hot to cold. High energy to low energy. That's why they repel, because as you push them together, you're trying to make the field stronger there, which means more energy there. It's like trying to go uphill on a slide. You're going to have to fight and do energy and work on yourself to climb a flight of stairs. That's just the way the universe works. Now, let us talk about the opposite situation. Let's talk about the situation where now I have two bar magnets. And instead of this, I put this as the North Pole here, and I put this as the South Pole here. You already know what's going to happen. Opposites attract, so they're going to come together. Let's see if we can understand it. The magnetic field exits and enters here, exits and enters here. It comes out here and enters here. It comes out here and it enters here. It goes out of the North Pole, always into the South Pole. So out of the North Pole, always into the South Pole. And then it goes out of the North Pole here, out of the North Pole here, and this direction, and into the South Pole here, into the South Pole here. Now I'm going to erase this one because I think this makes it confusing. But you can see the arrow. Actually, let me erase this one as well. I think it's going to be a little clearer if I put, yeah, like this, like that. So like this. Notice the direction of the arrows. When I bring these things closer together, notice that this one is going up, but this one at the same location is going down. They're fighting each other. And as I bring them closer and closer together, I messed up my drawing. I'm sorry about that. As I bring them closer and closer together, what is going to happen? This magnetic field is going to tend to cancel with that one and make the magnetic field strength lower. This one is going to be going opposite direction of this one, and it's going to tend to make the magnetic field strength lower in the center here. So as I bring these guys together, I'm going to write down weaker. As I bring them closer together, the field gets weaker in strength. But weaker in strength means weaker in energy storage. And remember, the universe likes to go towards lower and lower energy storage. So two magnets attracting can be explained. Because when we bring those two poles of the magnet together, we are canceling the magnetic field, making the magnetic field lower between them, which is a lower energy state. Lower energy, it's like releasing energy from the rubber band. The same way the rubber band comes together, the magnets come together, because as soon as that energy starts to get lowered, it is just going to fly together to make the energy lower. Forces in nature generally always push things in the direction of lower energy. Gravity pushes you down the slide to lower energy. The electric forces pull us to lower energy from the rubber band, and the magnets pull each other together or push each other together into a lower energy state together where the field is weaker. You feel a repulsive force because as we try to do this, the field is stronger and we're raising the energy here, and so it wants to resist that. Okay, that is about all I want to say about it. I can talk about magnetic attraction and repulsive in other ways. You can use relativity theory to talk about relativistic effects to explain why magnets work. And I probably will do that one day because I think it's a neat way to look at it. But it's just another way of looking at it, right? An alternative way of looking at it. You can also look at the magnetic force on a charged particle, the deflection of a charged particle from the magnetic force itself to explain why magnets attract each other. That's another fine way of doing it. I thought about presenting all of those, but ultimately I think that this is the most clear and elucidating, to use a big word, way to explain it. The universe likes to go from high energy to low energy. When you push two magnets together with the same pole, either both north or both south, the same exact thing will happen if you take this. If you can imagine the south pole over here, they're both going to be pointed in the same direction, and the two south poles are going to make a strong field, and it resists that. But if you flip it around, they're going to attract to make the field and the energy stored lower. Now, if you ask another question, well, why does the energy of the universe like to get lower? Well, I don't know, and nobody knows, all right? Or you might say, back to the electron spinning, you might say, okay, that's a neat theory about the electron spinning and how it explains magnetism, but why do electrons spin? I don't know, okay? And also, is it a ball? No, we know it's not a ball. Quantum mechanics is a wave theory. We know electrons are waves, but they have some kind of angular momentum, and nobody has a really good picture to describe how a wavy thing has an angular momentum, which we usually associate with spinning objects in the macroscopic level. Ultimately, one of my favorite people that I've ever studied is a famous scientist named Richard Feynman. Probably knew more about quantum mechanics than most people will ever learn, right? Way more than me. And somebody asked him, hey, explain to me why magnets work. And he thought about it and he gave about a 20-minute answer and ultimately concluded, I can't explain it to you because once you continue asking questions, you get down to the point beyond which anyone has any answers to anything. So all we do in science is we have models of nature, right? Do magnetic field lines exist? Not sure. They're a great calculational tool to calculate how things will behave though. Do electrons really spin? Not sure, probably not. But it's a great calculational tool. It's a good model of how the universe works. Maybe everything is string theory. Maybe everything is waving strings. Maybe angular momentum is something totally different than I can conceive of. but that doesn't make the theories and the ideas worthless. We come up with better and better models to describe the world. This is how I chose to describe how magnetism attracts and repels objects to you. When you bring a magnet next to the paperclip, it aligns the magnetic domains as we drew in the paperclip. And then now we've explained how magnets can attract and repel. And then of course they attract each other. So you're inducing a magnet to form and then they attract each other. And then of course we talked about this. If that doesn't satisfy you, well, join the club. It doesn't totally satisfy me either, but I think it's the best humanity can do with just making better and better models to describe our world. I hope you've enjoyed this. I know it was a bit long. I thought about cutting several things out, but ultimately I thought, you know what, I'll just put it out there and see what people think. So please drop me a line, let me know what you think, and if you made it to the end, thank you very much. Drop me your thoughts, and I'll see you in the next one. Learn anything at mathandscience.com.